Hello, everyone. I'm happy to be here and present our latest work, Faster Complete Addition Laws for Montgomery Curves. This is a joint work with Reza Rezaian Farashahi and Sohaila Sabagian from the Department of Mathematical Science, Isfahan University of Technology. Uh, well, this talk is divided in three parts. We first review quickly preliminaries, especially we talk about complete addition laws. After that, we introduce our new representation for Montgomery curves that is called extended Montgomery coordinates. And after that, we compare our result with previous complete addition laws. Well, it is well known that every elliptic curves defined over field such as f can be represented in P2 by the line Weierstrass equation, as you see. And if the characteristic is different to 2 and 3, then it can be represented by the short Weierstrass equation. The f rational points of elliptic curve are those points in P2 which satisfy this equation. And it is known that chord tangent process turns this set into an abelian group. Now, that is an abelian group, it has an identity element. This identity element is the point at infinity, and the negation of every point, such as x, y, z, is x minus y minus a1, x minus a3 z, and z. The core operation in elliptic curve crypto is the addition law. You are given 2 points, P1 and P2, and you are asked to compute P3. There are, first, let's have a geometric perspective toward this addition. Most of you knows it, but quickly review it. We are given 2 points, P1 and P2. The line that passes these two points has to pass the curve due to the Bezout theorem, and in the third point R, and the negation of this point is P3, that is P1 plus P2. And if P1 and P2 are the same, the tangent line passes the curve and the negation is 2P1. Now, if we formalize this addition, we'll see that there are different cases. If, for example, if Z1 is 0, P1 plus P2 is P2, and so on. So we have different if a statement. And if we want to implement this addition law, different cases takes different times, and requires different power, which causes some side channel attack. For example, now suppose that now we want to talk about the complete addition laws. An addition law is complete if for every given 2 points, P1 and P2, it can compute P1 plus P2. Without any separate consideration. What's the selling point of this addition law, complete addition law? It has efficient implementation. Second, it protects against some kind of side channel attack, such as simple power analysis. But the question that arises here is that if we have any complete addition laws for elliptic curves. Well, Bussmann and Lenstra in 1995 answered to this question. They showed that over the algebraic closure of F, there is no complete addition laws. They provided a set consists of a set of elliptic curve addition for elliptic curves that consists of 2 addition that can compute the addition of every 2 points, but it consists of 2 addition. They also characterize the addition laws by a one-to-one corresponding between the projective line in P2 and addition laws of by degree 2 and 2 on E. Okay, let's talk about twisted Edwards curves. We know that one of the most efficient form of elliptic curves is twisted Edwards curves. In and Twisted Edwards curves has a such equation, and if we are given 2 points P1 and P2, x1 y1 z1 and x2 y2 z2, and we want to compute this addition, the third point is computed, their addition is can be computed using this formula. And it is well known that this formula is complete if the product of A and D is a non-square element. The computational cost, if we count the multiplication, we will see that its computational cost is 10 m plus 1 squaring plus m stands for multiplication, s stands for squaring, and d stands for multiplication by a constant element. Its computational cost will be 10m plus 1s plus 2d. But we are looking for more efficient addition laws. In 2008, Hischel, in his PhD thesis, introduced twisted Edwards coordinates. In these coordinates, a twisted Edwards curve has such equations. In fact, it's the intersection of two varieties, and the addition laws has such a formula. This addition law is complete if the same as the previous case. If AD, the product of AD is a non-square element, but it's more efficient. It requires only 9 multiplication plus 2 multiplication by constant element. And in specific cases, its computational cost is 8m plus 1d. If we compare this representation with the previous one, we'll see that it requires one multiplication, 1 square, and 1 multiplication by a constant element fewer than the previous case, at least. Okay. But what's the Montgomery curve? Montgomery curves has such an equation, and it's we will see that its addition is not complete. I mean that when you want to compute its addition, we have to consider different cases, and so it is incomplete clearly, and its computational cost is for addition in the case that P1 is not equal to P2 is 13 multiplication plus 2 squaring plus 2 multiplication by a constant element. It is in the seminal work of Bernstein, Lange, and their co-authors, they show that there is a the family of Montgomery curves and twisted Edwards curves are the same. And they provided such a birational maps between these two families. Every twisted Edwards curves with the coefficients A and D can be sent to the Montgomery curves with coefficient A and B with this function, and can be returned back to the twisted Edwards curves with the other map. Now, in 2019, Kim and its co-authors, some of the other guys, try to, as we said, twisted Edwards curves has complete addition laws. We see here that we have only one equation, one addition laws for computing P1 plus P2. We don't have if statement, but for Montgomery curves, we don't have such a situation. In 2019, Kim and et al. Tried to provide complete addition laws for Montgomery curves. Their first approach was to use the complete addition laws of Edwards to extract the complete addition laws for Montgomery. As you see, they tried to send the points of Montgomery to the Edwards, formalize their additions, and come back the point Q1 plus Q2 to the Montgomery. But if we consider the previous map, we will see that for transferring points to from the Edwards to Montgomery and the other way, we need 3 multiplication for every transmission. So so if we want to do this, if we want to extract addition laws for Montgomery using these maps, we will see that this addition law results in an addition law with computational cost 19 multiplication plus 1 squaring plus 2 multiplication by a constant. But it's a first problem. When we check this addition law, we found that this addition law is not complete because of the exceptional points that we have in these maps. So we tried to find a map between Montgomery curves and twisted Edwards curves in such a way that we don't have any exceptional points, and we don't have any extra computations. I mean that we were trying to find a map between Montgomery curves and twisted Edwards curves such that we don't need any multiplication to transfer points between them. In that paper, they used the Buzma and Lenstra method and showed that in famous Montgomery curves, there are some small s that this polynomial is irreducible, and using the Buzma-Lenstra method, they showed that they can find complete addition laws for Montgomery's, but its computational cost was 14 multiplication plus 2 multiplication by a constant. As we can see, there is a big gap between the computational cost of twisted Edwards curves and Montgomery curves. The goal of this paper is to find a complete addition laws for Montgomery curves with the same computational cost. Yeah. So as I already mentioned, we tried to find a multiplication free map between Montgomery and twisted Edwards curves. To do this, to achieve this goal, we tried to embed the Montgomery curves into a projective space P3 instead of P2. The same method that Hishil considered for introducing extended twisted Edwards coordinates. To do this, we introduced new coordinates that we call it S, and we see that our Montgomery curves has three variables, U, V, and S. And now we can embed it into P3 by a simple substitution. And we can introduce extended Montgomery coordinates as you see here. Now, what's the advantage of working with this coordinate? Its advantage is that, as you see, if you consider these coefficients for twisted Edwards curves and Montgomery curves, there is a multiplication free map between these two curves. And the other point is that not only it is multiplication free, but also it has no exceptional points. So we can transfer points from Montgomery curves to Edwards, to twisted Edwards curves, compute their additions, and return back the points. And if we formalize, we will see that we can see here that there is no multiplication here, and the computational cost will be the same as the computational cost of twisted Edwards curves that we need for the complete addition laws of twisted Edwards curves. Yeah. And yeah. Now, suppose that we want to add 2 points, P1 and P2 in Montgomery curves. What we will do here is that it is worth mentioning that we use a new coordinate system also. This coordinate system takes a point and consider the points in this form. Yeah. Now, if we want to compute P1 plus P2, we consider the points in this coordinate. And as you see in the lower part of the slide, the multiplication is complete. I mean that we only have one addition law. And if we count the multiplication, we will see that it only requires 8 multiplication. And the only constant that we need to compute and multiple to T1, T2 is A minus 2 over A plus 2. It means that if we consider the Montgomery curve such that this constant be small, then the computational cost of this addition laws can be considered only 8 multiplication. To recap, if we compare our results with previous complete addition laws, we will see that we reach to the minimum cost between all the previous cases. The minimum, the best complete addition laws was is for twisted Edwards curves, that is 8 multiplication plus 1D, and we have the same cost for this for Montgomery curves. Thank you for your attention. Any question?
If you want to ask a question, you can come to the mic. Meanwhile, I will start with one. Can you elaborate a bit on the practical impact of these new formulas? Which applications would you switch from Edwards to Montgomery now?
In some cases, we only want to stick to Montgomery curves without going to the Edwards curves. So yes.
And which algorithm would you think would be targeted by this? Have something not natural in mind?
You know, these two formulas are the same. So I don't know right now exactly.
Maybe we think about that offline. There is a question there.
Hi, thank you for the presentation.
Yeah.
Could you go please back to the slide when you present the extended Montgomery?
Yeah. This one?
Yeah. There, I think there, the W is in denominator, so you don't consider the inversion of W to make the conversion?
Pardon?
Yeah, because when you make the substitution, you transform the coordinates, and then you introduce a denominator. So next in the slide, when you transform from Montgomery to twisted Edwards,
yeah,
there is no overrun, so the cost is for free.
Yeah.
Could you develop, please, again, why is for free this transformation? Because I didn't.
Because there is no multiplication here.
Okay.
There is no multiplication here. If you compare this to this slide, to this one, you will see that for a given x, y, z, if you want to transfer it to the Montgomery, you need 3 multiplication between x and z plus v, y, z and z plus y, and x and z minus y.
Okay, thank you very much.
Sure.
Any other questions, Mark? Yeah.
How are the addition costs competitive compared to Twisted Edwards?
Addition cost? It's exactly addition. It's exactly the same as the addition laws of Edwards. No. Just a moment.
I mean, like the number of ads used in the formulas.
I think that it's here.
There's no column for the number of
first
there's
line.
inside the. I'm just curious, like, if it used fewer adds and subtracts and the same number of multiplies, then it would be faster, right? Same number of multiplies but more adds and subtracts.
It needs
slower, right?
12 more additions.
Okay.
Yeah. Because of this transmission.
I see. Okay.
Yeah. Because of this transmission, we need eight additions to transferring and 4 additions for returning back the points. Yeah.
Okay.
That's the only difference.
Just for future reference for whoever watches the video in the future. So this was a question about comparing the costs of the formulas with regards to additions and subtractions too, when converting from Montgomery to Edwards.
Yeah.
Any other questions? So let's thank the speaker again. The next presentation is online. The work is load balance parallel implementation on GPUs for multi-scalar multiplication algorithm by Yutian Chen and co-authors, and Yutian Chen provided a pre-recorded presentation.
Hello everyone, my name is Yutian Chen from Wuhan University. Today I'm here to give a presentation on our work, load balanced parallel implementation on GPUs for multi-scalar multiplication algorithm. zk-SNARK is a cryptographic primitive that has gained significantly attention in recent years, allows the prover to generate a proof pi for any small MP relation. But most of elliptic curve-based zk-SNARKs like Groth16 and Plonk still suffer from performance bottlenecks. In particular, large-scale MSM operations occupy the majority of the computational cost during the proof generation phase. So we mainly focus our attention on the fast implementation of MSM. Owing to the thriving development of modern GPU architectures, we can also accelerate MSM operations by GPU. Okay, firstly, we should introduce what MSM is. Given n scalars k sub I and n points p sub I, the target is to compute the sum from I equals 1 to n, or k sub I times p sub I. Here, the double and add algorithm is a straightforward approach to compute MSM. It is similar to the fast exponentiation algorithm, but in the worst case, it requires up to n lambda p add and lambda minus 1 p double, which here p add means the point addition and PDBL means the point doublings. In real-world zk-SNARKs, the value of n is generally very large. So the parameter algorithm and its variants are in fact the fastest serial algorithms. It first chooses an integer c as the window size to decompose the main task into multiple subtasks. To complete each subtask, the parameter algorithm introduces a buffer point called the bucket and divides the subtask into 2 phases. The first phase, called bucket accumulation, is to get the value of bucket b sub t, which means the sum of all points with the subscalar equal to t. And the second phase, called bucket aggregation, is to compute the sum of t times b sub t using the serial method shown in this figure. However, there are still many challenges in parallelizing the parameter algorithm. For bucket accumulation phase, assuming the total number of threads that the GPU card can provide is uppercase N. The fundamental idea of the parallel implementation is that each thread processes consecutive and divided by uppercase N subscalars along with their associated point. But when different threads process buckets stored at the same storage in the buffer, write conflicts are inevitably encoded. There are two types of solutions in existing schemes. One is to adjust the edge to ensure that each thread processes non-overlapping data. And the other one is to directly allocate independent buckets for each thread without adjusting edges. But the former one can lead to load imbalance, while the latter results in large memory usage and cannot parallelizing the bucket aggregation phase. For bucket aggregation phase, it can be divided into two stages, the bucket updates and the final summation. The final summation can be accomplished using the well-known parallel reduction algorithm. However, it is evident that the bucket updating part, as shown in this figure, is a serial computational process. There are still no practical parallel algorithms proposed for this. Okay, so now we can describe our specific work. We give a figure showing our overall architecture. The main optimization points are in three stages: scalar processing, bucket accumulation, and bucket aggregation. The first optimization is inspired by the representation of floating point numbers. By this formula, the C bit subscalar k sub ij can be converted to a 32-bit representation head k sub ij. It includes three valid data segments here, an odd number of C-1 bits, an exponent of log base 2 of C-1 bits, and finally, a single bit sign flag. After that, we are able to change the way to add points into the bucket. Firstly, we can obtain pre-computed points based on the exponent part of head k sub ij. This relies on the fact that we can pre-compute several doublings of the point p sub I. Then, the points obtained from the lookup table can be added to the corresponding bucket, where the bucket index is equal to the odd number part of head k sub ij. If your GPU device does not have enough memory, you can also control the size of the pre-computation table using a threshold parameter top. It is evident that using this approach, the number of buckets is reduced to 1/4 of the original. The second optimization is to reduce the number of multiplications in the process of adding 1 or 2 original points into one bucket. After evaluating multiple coordinate systems like cached Jacobian coordinates and homogeneous coordinates, we mainly design two approaches. Based on the cached Jacobian coordinates as shown in the table, we can add a single point to the buckets within only 10 multiplications. It is the optimal choice for the single point approach. Fortunately, we find that adding 2 points to the same bucket per round further reduces the number of multiplications. Based on the homogeneous coordinate, we can achieve a double point approach that requires an average of only 9.5 multiplications per addition. The third optimization is our load balancing algorithm for the bucket accumulation phase. As mentioned before, unordered and random scalars can lead to a conflict where different threads write to the same bucket. So we don't adjust the edge, but instead relocate non-conflicting point buffers to both keeping load balance and avoid conflicts. Our modified accumulation phase can be divided into 3 stages. One is sorting the processed scalars. And the next is accumulating parts of the buckets into buffers. And the last one is utilize a variation of the binary search to aggregate buffered points back into buckets. For the design of the buffer, if we directly allocate a memory of 2 raised to the power of c minus 2, or n over uppercase n, this would cover all possibilities, but the memory would be too large and sparse. Know that the key is too sparse. So based on the fact that the subscalars have already been sorted, we set the starting write offsets for each thread using this formula. Here, we also provide an example figure, which shows that each thread can have at most one unused point space, making the buffer compact. The final buffer size is completely acceptable and independent of the scale n of the MSM. Let's have a simple analysis of the complexity. If the scalar distribution is uneven, our load balanced accumulation will have significantly lower complexity than the previous one. In a case where n equals 2 raised to the power of 24, we can achieve more than 1,000 times speed up. Besides, in the best case, which means the previous accumulation also luckily achieved load balance, the cost of our algorithm is nearly identical to it. The last optimization is our layered parallel reduction algorithm for the bucket aggregation. In detail, as we have 2 raised to the power of c minus 2 buckets, we can assign half the number of threads on each subtask. Then the aggregation phase can be completed in c minus 2 rounds. Look at this example. Assuming we have 4 buckets, b sub 1 to b sub 7. In the first round, one thread computes b sub 1 plus b sub 3, while another thread computes b sub 5, b sub 5 plus b sub 7. In the next round, we can use the intermediate results from the previous round to parallelly obtain the final result for the first 2 rows. This is clearly an algorithm within logarithmic complexity. The constant time property means that the running time is independent from the input. Since we used an algorithm similar to binary search in the final stage of bucket accumulation, this part is not truly constant time. Considering the more stringent security requirements in specific scenarios, we also provide a constant time patch for this. The basic idea is to process any 4 consecutive data according to this table. Based on the property of the subscalars being in ascending order, the capacity of this table only needs to be 8. Moreover, the cost required for each case is consistent, with each round requiring 2 p-add and 2 out operations. Here, the out operations means the memory copy operation. Ultimately, we can complete this operation within a logarithmic number of rounds. Here are our experimental environment and parameter settings. Compared to CUZK, an MSM GPU implementation presented at CHES 2023, we achieved approximately twice the speed up while maintaining the load balance property. We also evaluate the performance improvement brought out by our load balancing algorithm on the BLS 24 to 315 curve. As the MSM size increases, our advantage becomes more pronounced from over 20% to over 80%. Finally, we conducted a comprehensive evaluation of the constant time version, and the results show that for our constant time version, the running time in the corner case is almost indistinguishable from the average case. Additionally, it is important to clarify that although our non-constant time version is affected by the scalar distribution, the performance drop in the corner case becomes less noticeable as n increases. So users can choose either version according to their specific needs. Thanks for taking the time to listen to my presentation.
Well, we would have quite a bit of time for questions, but I can find the speaker online. So then, yeah, I don't think it's possible, but if any questions arise, please talk to the speaker offline. And then let's move on to the next presentation. That's Elastic MSM, a fast, elastic, and modular preprocessing technique for multi-scalar multiplication algorithm on GPUs by Zudong Zhu, who is presenting the paper.
Good afternoon, everyone. My name is Xudong Zhu. I'm going to talk about preprocessing technique for multi-scalar multiplication algorithm on GPU, and we call it Elastic MSM. In the first part, I'm going to talk about some background knowledge. First, I want to introduce the ZK-SNARK. ZK-SNARK is an application-oriented variant of zero-logic proof, and this is a framework. It has many applications such as this. It should satisfy the succinctness, which means that it has small proof size and fast verification. So someone may ask that, how about the prover's complexity? Unfortunately, in fact, the prover's efficiency is always one of the biggest bottlenecks in ZK-SNARK. And if we analyze the computation performed by prover, we can know that the multi-scalar multiplication, also known as MSM, is generally the main computational bottleneck for CK-SNARK-based proof systems. Okay, let's move to some common easy point operations. The first one, point addition, also known as PADD. This is a fundamental operation. And the second one is point doubling, which is also known as PDBL. This can be regarded as a PADD operation on two identical points. And finally, point scalar multiplication, also known as PMAT, can be regarded as K times cell PADD. Notably, PMAT can be computed through a serial's PADD and PDBLs. So we call the PADD and PDBL as the basic operation. Okay, if we combine the PADD and the PDBL, we can define the n lambda MSM just as this. Well, the n is the scale of MSM, and all the scalar Ki are lambda bit scalars. So how to compute this faster? In scenario involving SIG-SNARK, the state-of-the-art serial algorithm for MSM are the Pimlinger algorithm and its variant. We assume that the MSM scale is 5, the bit width of the scalar is 12 bits. Suppose that we want to compute the sum of these Qi. So first we can express all these scalars in their binary form just like this. If we set the window size to be 4 bits, then we can divide all these scalars according to these windows. And then we can obtain some independent subtasks just like this. Then in each subtask, we could add all the scalars with the same value into the specific bucket whose index is the same as the web. Then we can use this formula to compute the subtask result. Finally, we can use this formula to compute the MSM result. So can we use the GPU to further speed up the Pimlinger algorithm? Okay, the answer is yes. And there are currently some efficient parallel Pimlinger algorithm available. And there are some efficient implementation of MSM are now based on these algorithms. Okay, let's say the first parallel Pimlinger one. This is a natural method. Recall that during the Pimlinger algorithm, we can obtain some independent subtasks, just like this. So for n lambda MSM with S window size, we can arrange lambda divided by S threads to perform this subtask simultaneously. Okay, let's say the first parallel Pimlinger 2. This is a general method. Note that Q can be expressed as this large-scale summation. So we can divide this large-scale summation into T small-scale summation. They are independent. So we can use so for each small-scale summation, we can use a serial Pimlinger algorithm for computation. Then the third method is just the combination of the method 1 and method 2, just like this. And there are two more advanced MSM algorithms and GPU. The state-of-the-art parallel MSM algorithm recently proposed in this paper by Lu et al. Has achieved nearly perfect linear speed up over the Pippenger algorithm. Its ideal meaning includes the special parallel design and the application of sparse matrices. Very recently, Chen et al. Proposed several lines optimization techniques and introduced a novel GPU accelerated MSM algorithm. In this concurrent work, it leveraging this technique. This work achieved even significantly faster MSM computations on GPU. So can this algorithm be faster with preprocessing? Okay, the answer is yes, and I want to introduce a good preprocessing here. It is named as GJKP. This scheme is proposed by Ma et al. In this paper, and it can bring significant improvements to MSM computing and GPU. Okay, let's take Q1 as an example. The Q1 can be expressed as this, and equivalently, it can be expressed as this, right? Okay. Then GZKB told us we can pre-process all these points. And the other two are similar. However, this method, the drawback of this method is that it requires too much actual memory space overhead. So what should we do if our storage space is limited? Okay, in the second part, I'm going to talk about our contribution. Okay, let's say the elastic MSM. Generally speaking, the HQI can be expressed as this formula. And if we define lambda divided by S equals WK, then equivalently, the QI can be expressed as this vector multiplication. If we further define the capital M as this, then equivalently the QI can be expressed as this matrix multiplication. Okay, let's see the left part. We can multiply all this power of 2 and the point pi together to obtain the pi1, pi2, dot piw. And elastic SM told us that we can pre-process all these points. Okay, let's say the right part. This is a matrix multiplication. So this is equivalent to this scalars. So overall, the QI can be expressed as the sum of these points. Okay, with those that, so this is indeed a new MSM instance based on pre-processed vectors of easy points, just as this. So the elastic MSM still choose the same window size as. However, we consider the scale of MSM as Wn. rather than just n, and the bit length of the scalar as ks rather than lambda. So elastic MSM is a modular technique, just like this. It provides a flexible adjustment between the scale of MSM and the bit length of scalar, but at the cost of preprocessing. Notably, almost all existing parallel MSM algorithms are faster with larger scale MSM and the smaller bit length scale. For example, let's see the mean complexity of CUZK. From this figure, we can do that. This term is fixed. So if the lambda become smaller, then the overall complexity becomes smaller. Okay, this is the preprocessing overhead of elastic MSM. Note that both of the W and K are flexible parameters. So elastic MSM provides a trade-off between the time and the space saving. Okay, let's see some special parameters. If we set the W equals 1, then there is no preprocessing at all, and the elastic MSM degenerates into the ordinary process in Pippinger algorithm. And if we set K equals 1, then the W reaches its maximum value. This is essentially the preprocessing of GCKP. Note that GCKP has also provided a checkpoint strategy to better balance time and space saving. However, it could lead to even more fatal problems. Let's see this table. The flexible parameter M in GCKP can be used to balance the space and time. However, this term is very large. It will impose an unacceptable burden on MSM. Okay, let's see the application of elastic MSM. As we discussed above, the elastic MSM is a modular technique, so it can be directly applied to a several parallel Pippinger algorithms, just like this. Okay, let's see the evaluation. This table shows us the performance results about approach 2 across various storage space limitation. From this column, we can see that when the storage space is limited, the additional MSM overhead caused by the preprocessing in GCKP is very high. And from these two columns, we can see that elastic Pippinger has faster preprocessing speed across various storage space. And from these two columns, we can see that elastic Pippinger 2 achieves up to about 1.9 times speed up across various storage space. Okay, let's see this table. This table shows us the results about approach 3. From these two columns, we can see that elastic Pippinger 3 achieves up to about 1.08 times speed up across various storage space. Okay, let's see the combination of CUCK and the elastic MSM. We call it elastic integer 4. It achieves, we can see that this is the CUCK, and we can see from this column that elastic Pippenger 4 achieves up to about 1.36 times speed up across various storage space. Okay, if we fix the actual space overhead to be this, we can, let's see the performance results about approach to across various MSM scale. Elastic Pippenger has the fast from these two columns. We can see that the elastic Pippenger has faster processing speed across various MSM scale. And from these two columns, we can see that elastic Pippenger 2 achieves up to about 2.58 times speed up across various MSM scales. Okay, let's say this table is about approach to and across various MSM scales. The let's see these two columns. We can know that elastic Pippenger 3 achieves up to about 1.39 times speed up across various MSM scales. Okay, this table shows us the elastic Pippenger 4. From this column, we can see that elastic Pippenger 4 achieves up to about 1.91 times speed up across various MSM scale. Okay, that's all. Thank you for your attention.
So the speaker is online, so let's thank for the talk.